problem that we were going to work, this one, yeah. At the end on last time that we didn't quite get to, so let's start there. It was, okay, these guys here. All right, so this is the last page from Wednesday. All right, so we were given that limit as x approaches 9 of f of x is 6. Limit as x approaches 6 of f of x is 9, and that f of 9 is 6. We're also given x approaches 9 of g of x equals 3. Limit as x approaches 6 of g of x is also 3. And g of 6 is equal to 9. Okay. And then we're asked to compute a whole bunch of things there. Okay, so for the sake of time, first off, well, let's just kind of go through them. So what should A be? Yeah, so that's going to be whatever 6 plus 3, right? Okay, and then B would be x approaches 9, so f goes to 6. So on the top, we've got 3 times 6, and on the bottom, we've got 3, so it'd be 6, right? So those ones are easy. Okay, so the one I want to really kind of concentrate on are E, F, and G, because they're kind of nasty because of the function composition. Okay, so let's do limit as x approaches 9 of g of f of x. Okay, so first off, what does this mean, g of f of x? Yeah. Right. So you take an x, you plug it into f, you get some output f of x. You take that thing as an input and put it into g. You crunch whatever you get, and it spits something out, and that's the result. Okay. So this is function composition, right? Plugging one thing into another. Okay. Now, with respect to limits, what is this going to be? Well, what we can do is slip the limit inside the function. Okay, so what is this limit? So this is our question. What was this given to be? 6. Okay. And so that's okay. Do we know g of 6? Yes. It is what? 9. So this limit is 9. Okay. Now, this only works if two things, right? This limit had to actually be a quantity that we that existed and that we also knew, right, or could figure out, okay? And the function g, the outer function, we actually had to be able to plug 6 into it, okay? If either of those things were not true, then we would have a D and E type situation, right? Yes. That was given right here. Okay, so that was an assumption. Yeah. Okay, now in this case, we don't know what the function's equations are, right? We just know that they have these properties. No, that's from last time. Were there any extras floating around from the stuff from today, or can I just not count? Is that an extra? Okay. Give one to him and give one to me. I was pretty sure I could count. I mean, not to play the mathematician card, but kind of a mathematician. Actually, that means we're the worst at counting. Nothing is more hilarious than watching a bunch of mathematicians go out to dinner and try and split a check. It's a train wreck of epic proportions. So usually we end up just resorting to the easy solution, which is you take the total, you divide by the number of people at the table, and the weight, the staff brings the appropriate checks to everybody. But yeah. Um, okay. Um, Now let's contrast this with a very similar, but not identical question, namely, what's the limit as x goes to, well, okay, we're going to 6 this time, but whatever. Okay, so before we worry about the limit, what's the difference between, oh, and I'm sorry, the screen isn't down. Um, what's the difference between g of f of x and f of g of x? Yeah. Yeah, who's on the inside this time? G. Okay. So f of g of x and g of f of x are not necessarily, and quite often not, the same thing, right? Because it's an order thing of who you plug into whom. And on occasion, rare occasion, you get the same thing, and that actually means something if that happens. But do not assume that it's going to happen. Okay. And in this case, well, even if they were happen to be the same, it doesn't matter because we're approaching 6 this time rather than 9. So, why should we expect that everything's going to be the same? All right. So, two things we need to know. What's the limit as x goes to 6 of g? Was that a given quantity? 3. Okay. And so we knew that limit as x goes to 6 of g of x was 3, was it? Yeah, okay. Okay. Do we know f of 3? No. Okay, so this limit um, is, um, let's see here. Well, I'm not sure if I would say it's undefined or D and E. It's just cannot be determined. Let's say it that way. From the given information. Right? And the reason is because we don't know what f of 3 is, right? It's undefined. Okay. Uh, if we did know what f of 3 was, including whether or not it was like, let's say that the function f, when you plugged 3 in, you got a division by 0 or something, right? If we knew that, then we could answer this more proper. Okay. Um, okay. So then, what about g on there? So G was, just to keep things spicy, x goes to 6 of G of f of x. All right, so now we've got triple function composition. Oh, how fun. Okay, so what's the limit as x goes to 6 of f, the insidemost thing? 9. Do we know f of 9? What is that? Do we know g of 6? Yes, what is that? 9? Okay, so the whole thing comes out to be 9. So you see how we kind of chained it together like that? Yeah. Okay, good. All right. So that dispenses with everything from last time. All right, so what did we get here? 9. Yay. Okay. All right. Question preguntas fragen? No? Good? Okay. All right. So that's done with last time. Let's move on to the one-sided limit stuff. All right. So what's today? The 28th. Okay. So at first, one-sided limits are like, I've always actually found it kind of ironic that we should really start with one-sided limits and then do two-sided limits. But for some reason, every calculus book I've ever seen goes the other direction. Okay, I don't know why, but anyway. Okay, so the notation here, right, is that should be an A. Okay, the plus and the minus are written kind of like an exponent, so they're kind of up and to the right of the A. And the plus means from the right, and the minus means from the left. Okay. Now, you have to be a little bit careful when you're reading this because let's say that you've got A is negative, and B is or something, right? You could have -5 from the left, right? So you just have to. Sorry, you could have -5 from the left, correct? Yeah, okay. Shouldn't use left and right for stuff. Okay, so hang on a second then. Oops, and I put an equals where I should not have. Hmm. Was that what you were going to say? Oh, okay. Too slow. Caught it first. Um, okay, so, right. So the plus, like, don't necessarily think of it like the numbers could be negative, even though you're approaching from the right hand side. So the plus is sort of indicating from the right or the positive direction. Um, it's maybe not the best notation we could have come up with, but it's what we got. So just deal with it. Okay, so is that all right? So, so in some sense, right, when we were doing, I'm so sick of these masks. It's not even funny. And perhaps, you know, no, it did not. Clearly, it did not. And this thing's like brand new too. Yeah, I guess I could do that. That's a little ghetto, though. Let's try that. And guess what? It's out of staples. Okay, excuse me one moment. I'm having a wardrobe malfunction. I just tried, but the one in there is out of staples. So, you guys remember the wardrobe malfunction in the Super Bowl? Maybe you're a little young for that. Yeah, yeah, I forget who it was, but because it was the worst thing ever that somebody might see a bared breast on television, you know. Whereas we have TV shows that involve violent, gruesome murders, but you know, heaven pretends somebody see a normal piece of the female anatomy. Um, okay, so one-sided limits. Now, the reason I wrote M and N here, or sorry, L and M, is because these two numbers could very well be different things. Now, in a lot of situations, they'll end up being the same, but they could theoretically be different. Okay, so let's look at the graph that's up there at the top left of the page here. Um, and just figure out all four of these things. So take a minute and think about those four things while I write them down. Okay. Oh, sorry, Jaden. Yeah. So we have established that in fact I can't count. Are we missing anybody today? I feel like we are. Yeah. One. Okay, because there's 4, 8, uh, 13, 17, 18, and then Eddie. Okay, yeah. Eddie, did you get one? Okay. All right. So we've got all these four quantities. So take a minute and compute them all. Just kind of look at it. Nope. You. And let's make sure we all agree on them. Okay, so what do we get for the limit as x goes to 3 of f from the right? 3. What about from the left? 2. 5 from the right? 5. 5 from the left? 3. Okay, agreement, since I don't have the graph in front of me. Okay, so these two things could very well equal different numbers. Okay, now while we're on the subject, let me ask two other related questions. What are those two quantities, f of 3 and f of 5? Okay, now I heard D and E, so let's make sure that we are in agreement here. And let me see the graph just so I can double check. Um, yeah, okay. So 2 as x approach, or sorry, for f of 3, and 4 for f of 5. Okay, now how do we know that here? Because both of them have a dot, right? The filled in one. Okay. Okay, so are we good with that? So, all right, so what did we say it was? F of 3 was 2, and f of 5 was 4. Okay, so, oh, that is the worst looking 4 ever. Yeah, that's better. Okay, so the salient point here is that, as we saw, the value of the limit and the value of the function could be very different things. And the one-sided limits could also be different. And so, like at 5, notice what happens. All three of these answers are different quantities. Okay, and that can totally happen. What about on the, as we were coming at 3? Well, 2 of them happen to match, but the third one didn't. Is it possible for f of 3 to be undefined? It wasn't in this graph, but could it have been? Okay, and how would we have modified the graph to make that happen? What would we have to change about the graph to make f of 3 undefined? Yeah, make it a whole, so sort of erase the dot kind of thing, okay? Or over there at 5, we could have just erased that dot, and then f of 5 is undefined, okay? And yeah, now the other thing is that, as we saw last time, limits can also fail to exist, okay? And we'll talk more about different ways that they can fail to exist. In this particular case, all four of the limits, the two from the 2 at 3 and the 2 at 5, all worked out, even though they came out to in well, both cases, different answers, right? So that can happen. They could fail to exist. One of them could fail to exist. The other could be okay. And it just, basically every conceivable combination of things working and not, all of those can happen. Okay. Okay, good. So, all right. So let me see what's next here. Okay. So the big theorem here is what's the relationship between one-sided limits and sort of regular, or we might call them two-sided limits. Okay. So limit as x approaches a. All right. So let's say suppose limit as x approaches a from the left is L, and limit as x approaches a from the right is some number m. Then the limit, okay, so notice that there's no decoration on the A there. Okay, so the way I like to think of that is that I'm sort of coming from both the left and the right sort of simultaneously, right? Under what conditions does the limit exist? Only if the left-hand limit and the right-hand limit individually exist and equal the same number. Okay. Now, who thinks that I can't spell? Julius, you think that I cannot spell. What word do you think I misspelled? If. Okay. Huh? Double F. It's a double F. Okay. So why did I write if with a double F? And it's not because I haven't had coffee and I'm incompetent. Both of those statements are true, but that's not why I use two Fs. Uh-huh. Yeah. Jaden, do you remember? If and only if. Okay. So if and only if are two different logical connectives, right? So it's about implication, right? Assuming thing A, if thing B means thing B implies thing A. And only if means the implication goes the other direction. And often in mathematics, the implications go both directions. And so in English, we would say if and only if. But us being stuffy mathematicians and doing this all day means this comes up so often that we abbreviate it IFF for if and only if. Okay, because we're lazy. So, yeah. Now, has anybody taken the symbolic logic class in philosophy or Math 108 or that you guys that are wanting to do computer science? You guys will do this eventually, where you'll study a lot more about sort of predicate logic. And yeah, okay. Question? No. Okay. Your hand was sort of moving in a I'm about to ask a question kind of manner. Okay, good. So if we want to check if the limit exists, oftentimes what we can do instead is just check the left-hand version and the right-hand version and see if we happen to get the same thing. And if we do, great. And if not, the limit fails to exist. Okay, good. All right, so returning to our example graph, what can we say about the limit as x approaches 3 or as x approaches 5? They both fail to exist. Okay, so D in E for does not exist is usually, sort of how you would write that. And it's because, what did we get on the, as X was approaching 3? We got 3 for one of them and 2 for the other, and those are different numbers last time I checked. And what about over at 5? 5 and 3 are also different numbers. Okay, so in this case, neither of them worked out, but that, that was just sort of coincidence based on which function we had there. Okay, they could work out just fine. And in fact, it's possible for each of the one-sided limits individually to fail to exist. In which case, well, if the one-sided ones fail to exist, the two-sided one is sort of doomed. right? There's no way it's going to exist. Okay. Okay. So does that kind of make sense? Yeah. All right. So let's flip over to the next page. And let me just double check it here. Okay, so we got kind of a crazy limit going on here, and we'll talk about the zero thing later. So why don't you guys take a minute, couple minutes, and confer with your table mate. And those of you who do not have a table mate, make a friend real quick on the exercises on the second page, and then we'll go through and make sure we've got the correct answers. S'il vous plaît. And while you're doing that, I'm going to print out one more of these things so that I actually can see what I'm doing. And actually, I'm going to print out two since we're missing somebody. The last one. Yeah, that one's fun. Okay. So actually, this gives us a good opportunity to explain these things. So it's not that we're about to have a party and I've got a keg, but, and it looks like I need to go get a few more of these. All right, so the cups, and in fact, I need to start to condition you guys to grab a set when you come in. So what's the point of the cups? Well, sort of, or where you are and stuff. So when we're working on things like this together, what I want you to do is use the cups as sort of a color code for your current status. Yellow on top means we're working, we're good, leave me alone. Okay. Red means I could use some help or I've got a question. And green means we've got the task completed. Okay. And we're good. We've got it. Okay. Does that make sense? Yeah. Um, and this way I can kind of visually quickly survey you guys and see what status you're all in. And if somebody's got questions, I mean, obviously, yeah, you can raise your hand too, but this makes it real easy for me to scan the room and see where everybody's at. Yeah, isn't this brilliant? And those of you who like country music probably like the red solo cup the most, right? Because it fills you up, or you fill it up, or whatever, however the song goes. Um, you know, the quality of country music has really declined because when I was a kid, it was whiskey drowning and beer chasing, and now it's stupid stuff about red solo cups. Um, or better yet, so I've seen this one. With the advent of self-driving cars, it's only a matter of time before we get a country song about a guy whose truck leaves him. So, huh? Yeah. Well, probably yes. Right. He'll go live in a van down by the river. So, anyway, all right. So, what did we get for these? Do we have green? Are we all green? Are you guys green? Yeah, you got to use the cups. Right. All right. So for x goes to 4 from the left, you guys got 3. Good. 4 from the right, 4.5. Good. X approaches 4 because the previous two were not the same number. X approaches 5. Okay. X approaches 2. Does not exist because, yeah. So what is it from the left? What is it from the right? 3, and those aren't the same number. Okay. And then the last one's kind of weird. What'd you guys think there? Does not exist. Okay. That one's weird. And the way to sort of think about this is, so let's actually flash back a moment to the warm up for Wednesday. You remember there was the question about sort of the viewing window and sort of what were the bounds that needed to have on the viewing window. So that actually was kind of sussing towards the what the true definition of limits are, which I could write down and it would be gobbledygook and impenetrable to you guys because it's just a bunch of symbols. But essentially, the idea is the limit exists if pick a small number. Okay, you think the limit is some number. Go up and down by 0.3 from your number along the y-axis and draw a band. Okay, so that's like the vertical part of the viewing window from that exercise. Can you find a window around the x value that you're approaching so that if you're within that small quantity of that x value, you're guaranteed to land in this box? If so, for no matter what tiny number you pick, the limit exists. Okay. And if not, it doesn't. Okay, so thinking about that in terms of the viewing window, okay, what's going to be the problem? So, um, first off, just from the picture, okay, is it clear that there's no way the answer is something bigger than 2 or less than -2, right? Okay, those we can just rule out entirely. Okay, so let's say that we picked some random number between -2 and 2. Okay, that's a logical number. Okay, now pick a small number to be our Y viewing window. Okay, so let me go to Desmos actually, or actually I'll do Wolfram Alpha. Well, actually, I think I want Desmos after all. Okay, so we want, oops, Y equals functions sine of 1 divided by X. Okay. Okay, so there we go, right? And it's a little bit obscured here, but, oh, and I want to do 2 times that because of the scale. Okay. All right, so you picked the point 0, okay, and you also picked the viewing window up and down by 0.5. Okay, so what I need to do is I need to sort of zoom in so that we have negative, or sorry, 0.5 to negative 0.5 in our viewing window, and it'd be like this. Okay. All right. Is there an X box that I can draw around 0 so that if I stay within some number of units away from X, I always land within this box? And the answer is no, because, well, where is such a point? What happens to the graph? So here's my band, right? Where's 0.5? That's 1, so be here, right? The little band you picked is there. If I'm within any number of units of 0, do I get outside this band? Yeah. Okay. So the limit isn't 0. Similarly, could we have done this game for any other number between -2 and 2? Yeah. And they would all fail for exactly the same reason. Yeah? Okay, so this limit fails to exist. Okay. Now, I will grant this is a really wacky one, but yeah. Anyway, and just if you were curious about the formula that generates this particular graph, it's sine of 1 over x. Okay. And there's another way to sort of think about why it wiggles the way it wiggles. So you guys remember in trigonometry when you talked about like the frequency of if you had a sine graph, you could talk about its period or its frequency. Is this ringing a bell? Ding, ding. No? All right, well, let's talk about what does frequency mean in the context of sound? Yeah. Yeah, so from a physical standpoint, it's the distance between the peaks of the waveform, okay? And in terms of like actually hearing it, how do you distinguish the difference between pitch? I just gave it away. It's pitch, right? So my voice is at a lower frequency than this voice, which is at a higher frequency, right? So higher frequencies correspond to higher notes in the on scale, right? And essentially, what this sine wave is doing is the frequency is increasing basically to infinite, right? And so it's wiggling infinitely much, and that'd be like an infinite frequency. Now, that of course can't physically exist in the world, but when have mathematicians let the real world get in our way? Yeah, I mean, we're the people who come up with imaginary numbers, for crying out loud. Like, where are you going to go off and find those at a grocery store? Yeah. So anyway, okay, good. So let's. That one's a little weird, I grant. But yeah. Okay. So let's go over to the one at the last page here, and we'll kind of spend the last few minutes on this. So Dr. Insaldi claims that these are the answers, the things in red. Is she correct? Some of them? Or are they complete garbage? Okay, so let's go through these and try and figure them out. Okay, so again, grab the cups. So put your cups all in yellow to start, right? Because you're working, you're cool. You want me to leave you alone? Yeah, red means you need some help. Green means you're finished. Yellow means you're working and you want to be left alone. Okay. Now, this one's a little tricky though, because what do you have? You've got two graphs, not one. One graph for F and one graph for G, and we have to combine the information carefully. Okay, so does that kind of make sense, the task? All right, so go through a couple of these, and then we'll come back together and see if we agree with Dr. Insaldi or see if she's, like me, completely incompetent. Okay. And it's more than if she's right, why is she right? And if she's wrong, why is she wrong? We? What'd you bring me? A donut holes. Oh, man, you got a lot of balls. Bringing. Okay. Yes, sir.
So,
You got to put the solo cup to red, man. Yeah.
so for problems like these,
hmm
where they're crossing a two, but they have 2 points, would is this?
So what that means is we have to split this question into two questions, right?
Mm,
And do the left-hand version and the right-hand version separately. So in order to answer this question, because you're right, right, the answer looks like it could be different on either side, we need to check the limit as x goes to 2 from the left of this quantity and from the right of that quantity. And if we get 0 for both of them, then this is correct.
okay.
Okay, does that make sense?
So you just use this for plugging both numbers.
Well, but come from the left and from the right separately, right? So it splits the question into two pieces.
Gotcha.
Yeah.
And then for this, we would use 0 for g of x.
Uh, yes. In that case, it's the same for both directions,
Okay.
right? And if you think about it, that's why it's going to work. So even though the number here and the number there are different, if you're multiplying them by 0, what's going to happen?
0.
You're still going to get 0.
Yeah.
And that's why this one works out, even though when you looked at their graph, you're like, wait a minute, something's not right. Okay.
Gotcha.
And it's only because that number was 0, right? But yeah, so if something looks sus, you got to split it into two pieces, answer each piece individually, and then see if they happen to be the same thing. And if they are, well, great, right? And if not, well, sorry, right? Yeah, good?
Yep.
Okay. Yeah, of course. Okay. Green cup, good. Yeah. Let's see, where did I put my sheet? There it is. Okay. Okay. Yeah. Okay, so I think we're probably close to done here. Is Dr. Insaldi right on all of them? Ah, which one do you guys disagree with? All of them? Really? Except for six? Wow. Okay, well, let's go through them. All right, so let's look at number two. Okay, if we approach two from the left, what is G doing? G's going to 0, and F is going to 1. Okay, what's 2 divided by, or sorry, 0 divided by 1? Okay, what about if we come from the right, what is G doing? It's going to 0, right? And F is going to, what's 0 divided by -1? So they're both 0. So she's correct. Hmm? Why not? Oh, okay. Yes, I see your point. But it does actually exist. Okay. And the reason being, the limit as x goes to 2 exists if the left and the right hand limits are the same. Are they the same? The left and the right hand limits? For the whole function, not for f, but for g over f. Yeah, okay. So this actually brings us to a good point, which was the theorem. We have to make sure that we're clear on the theorem that we are used from last time. Okay, so the theorem from last time said if limit as x goes to a of f of x equals L and limit as x goes to a of g of x equals m, then limit as x goes to a of f over g equals L over m, provided m is not equal to 0. Okay, so Jaden's point is, wait a minute, for this problem, the two individual limits don't necessarily exist. It did for G, but it didn't for F. So how can this be true? Well, it's because of the logic here. And so to sort of illustrate that, like here we have a statement where the if condition is not true, right? Because for the theorem, we required that both individual limits existed. Is that the case for that problem? That as x approached 2 for both g and f. It worked for g, you got 0, but what was the limit as x goes to 2 of f? Does not exist. Okay, that's not equal to a number. Okay, so this the hypothesis of this theorem is not satisfied. That means we can conclude absolutely nothing. Maybe it works, maybe it doesn't. Okay, and here's why. So let me make a totally different statement. If I win the lottery tomorrow, then I will give each of you $1,000. Deal? Sounds like a pretty cool deal? Okay, so let's suppose that tomorrow I win the lottery and you guys all come in Monday morning for class and I start handing out stacks of Benjamins. What can you conclude? False. You cannot conclude that I won the lottery. How do you know that I'm just not rich and a really nice guy? Okay, but it didn't mean that I was going to give you $1,000 only if I won the lottery, right? How do you know I'm not like Scrooge McDuck and swimming in like a pool of cash back at my house? Okay, now, I mean, I'm being a little facetious here. You guys, of course, know that I'm not doing that, right? Okay, but if I handed everybody $1,000 on Monday, you would guess he probably won the lottery, right? Because where else would he have come up with that money? But can you guarantee that I won the lottery? No. Okay. Maybe let me give you a less flippant example. If it's raining, I will carry an umbrella. Okay. So let's say that you see me and I've got an umbrella in my on my bag. Can you conclude it's raining? No, not necessarily. Maybe I carry an umbrella all the time just in case, right? So that's basically what's happened here. Is the hypothesis was false, and so the conclusion, well, I don't know, maybe it works, and it turned out in this case it did work. Okay, all right. So I guess we're out of time. So I'll see you guys on Monday.